Hey, thanks, John. So, as John said, I'm going to talk to you today about using zircons to see through intensely altered rocks in porphyry systems using the case study of the Moroni magmatic corridor in northeastern Greece. And over the past few days, we've had a lot of great talks about using zircons in this kind of situation, so hopefully I'm going to be able to build on that this afternoon. But first, I just want to give you a brief introduction into the Moroni magmatic corridor and the geodynamic setting and the geochemical setting that we're in northeastern Greece. So if we look at the global distribution of porphyry copper deposits, we can see that generally they're associated with volcanic arcs, but in the Tethyan belt, post-collisional porphyry copper deposits become really important. Now, these are porphyry copper deposits where the magmatism is generated in a post-subduction setting, so we still have residual metasomatized mantle wedge beneath the systems, but we're not actively subducting at the time of magmatism. And these are becoming increasingly important because of the extraneous metal endowment of these systems, particularly in platinum group elements and semi-metals, and they're becoming increasingly important in greener technologies. So our understanding of these systems is really going to need to develop in the next few years. So if we look at this map of Greece here, we're looking in the northeastern portion of Greece, and in grey here we have the rhodope metamorphic core complex. Now, the rhodope metamorphic core complex is a portion of the lower crust that was exhumed up to the surface during Aegean transcrustal extension in the Eocene and Oligocene. And then the Moroni magmatic corridor is some contemporaneous magmatism that occurs right in the southeastern corner over here at the edge of what's locally known as the Ketcharos Dome. That's a northeast trending belt of intrusions that host porphyry-style mineralization associated with the hexagons, and then there's two epithermal deposits that Eldorado Gold are currently working with. And the geology of these of the porphyry systems, which is what my PhD has been focusing on, can be simplified into host intrusions that range from diorites to granites in composition that are then cut by late metal-bearing porphyry intrusions, and the mineralization is pervasive throughout the porphyry intrusions and is generally concentrated at the edge of the intrusions at the contact between the two igneous lithologies. So first, I just want to talk briefly about the host plutons and whether we're generating the right flavour of magmatism for porphyry-style mineralization. So throughout the presentation, everything's colour-coded, so anything relating to Leptocoria in the far northeast is in yellow, Cassiteres is in blue, and Moronia down in the southwest is in pink. So if we look at the host pluton geochemistry, they follow a calc-alkaline trend, and as we go from Leptocoria, which is the oldest, towards Moronia, which is the youngest, we move from a high potassium calc-alkaline series towards a shoshonitic series. So we're increasing in incompatible elements with time in the system. And if we look at the petrology and host rock geochemistry, in green underneath we have the geochemistry of the Andean igneous rocks from the Mamani compilation, and you can see that as aluminium increases with fractionation to an inflection point at around 56 weight percent silica, and then decreases. And this inflection point is where we saturate in plagioclase, and in the early stages of fractionation, we suppress plagioclase, and that's due to the elevated water contents in arc magmas. But in the Moroni magmatic corridor, we don't really see this. We kind of just see decreasing aluminium contents as we go progressively towards higher silica values, and we think this is because we're never suppressing plagioclase. We are in a drier system, so we're just crystallizing plagioclase from the onset of fractionation. But we do see some some hydrous phases. So we have primary hornblende phenocrysts, and then we also see granophyric textures in Leptocoria and Cassiteres, and this is where we have rapid crystallization beyond the eutectic point of these systems. And then as we move to Moronia, we actually lose our hydrous phases, and we just have primary clinopyroxene, and then all of our amphibole in the system and biotite is their secondary breakdown rims. So we're not seeing any hydrous phases in the later stages of magmatism in the area. But if we look at the trace element geochemistry, it's fairly similar to what you'd expect from an arc-type magma, so we're elevated in large iron lithophiles, depleted in high field strength elements. So we can use this to kind of infer that whilst we might be slightly drier than we'd expect to be in an arc-type magma, we still have the trace element composition that we'd expect to get from a metasomatized mantle wedge, and so we're melting a residual mantle wedge that is existing from earlier subduction in the region. And then if we look at the duration of magmatism, as we've heard, the duration of magmatism in the area is quite important for generating porphyry copper deposits, again, we're coming up a bit short. We have a short period of 800,000 years where we're generating magmatism in the northeast. Then we have a 2.5 million year break in magmatism where we don't see any intrusions. And then we have the change in geochemistry is 2.5 million years later with the intrusion of Mironia-Pluton. So do we have the right flavour of magmatism? Well, we have a calc-alkaline trend. We show evidence of an enriched mantle source. But we have short periods of magmatism. We're drier than we'd want to be. And also, we don't see the kind of strontium adiabatic signatures that you see in arc-type systems. So now, moving on, I want to talk to you about the petrogenesis of the metal-bearing porphyry intrusions. Now, this is obviously really important when we're considering where these metals are coming from and understanding mineralization in these systems. However, we come across a bit of a problem in northeastern Greece. There's no drill cores through the porphyry systems, so all of these rocks are hugely altered, so we need to find a way of seeing through the alteration. And A is the freshest porphyry intrusion that I have from the field area. You can just about see the porphyry texture, but B is much more representative, and there's no kind of original mineralogy and texture left there, so we have to find a way to kind of see through this. And as Matt really nicely introduced earlier, zircons are an excellent way of doing this. They're a really robust mineral phase, and they record the changing magma geochemistry during crystallization. Now, there's 3 data sets that I've been using from zircons to kind of get at this petrogenetic history. First is the geochronology, second is looking at trace element geochemistry, and the third is looking at melt inclusions that I found within the zircons. So before we dive into the geochronology, just need to have a look at the morphology of these zircons. So the porphyry zircons tend to have these really distinct cores that you can see here, and evidence of resorption and multiple phases of crystallization in these porphyry zircons. Whereas the plutonic zircons tend to be, or they all are very simply oscillatory zones. So we're not seeing this like dual phases of crystallization that we get in the porphyry zircons. So then when it comes to doing geochronology on this, we kind of come in a bit of a bind. We want to have really high spatial resolution, which is where laser ablation work comes in really handy with the kind of 10 micron spot, but then you end up with low precision. And if everything's happening very quickly, we need this high temporal resolution to see the changes that are occurring. So then we can use ID TIMS, but if we are diluting a whole grain, we're homogenizing and we're integrating across this crystal, and that's not something we want to do when we can see evidence of inherited cores. So what we did instead was to fracture the crystals, so we just dissolved the tips of the crystals, and then we dissolved the cores of the crystals, so that we could get the high precision, high temporal and spatial resolution on the dates so that we can make valid interpretations. So here there's 2 separate points that I want to make. So this figure on the left shows a zircon with a distinct core and rim, and the rim is Oligocene around the same time of intrusion as the host plutons, but the core is Cretaceous, early Eocene, late Cretaceous. So we have this distinct inheritance. We have 2 different phases of crystallization that we're observing in these zircons. And then if we just consider the rims, when we consider the rims of these zircons, this is all of this data along here. In grey is rim ages from the Cassiterese porphyry. And these rim ages are actually older than the Cassiterese host intrusion. So this means that the zircon rim ages aren't just reflecting the time of emplacement of the porphyry, but they're reflecting protracted crystallization before the porphyry is emplaced. And that we're seeing that crystallization and uranium-led dating isn't just dating emplacement, it's dating a period of magma storage as well. So we can come up with a bit of a model for the systems by looking at just through the geochronology, and that is that we have some kind of reservoir in the crust that's crystallized in the Cretaceous, and that's still probably some kind of mush system. And then as we intrude our host Pluton through the system, we begin to generate small volume melts, and then we emplace these small volume melts that kind of are a hybrid between this deep crustal body and the new magma that's been introduced into the system. And so we can look at the trace elements in the zircons to kind of evaluate this. So this is a plot from Nick Gardner's paper looking at the tin tungsten belt of Myanmar, and he uses uranium over ytterbium as an indicator of crustal contamination. So this white line here shows what you'd expect in a MORB source, and anything elevated above that shows increased crustal contamination into the magmas. And in orange is Nick's compilation from Myanmar, and then in green is the Liu compilation of porphyry zircons. And we can see that actually the zircons from the Moroni magmatic corridor overlie both of these quite nicely. So then if we look at the rare earth elements of these, in green again we have the Liu compilation, so a porphyry exemplar, and you can see a really flat europium anomaly. This is from the suppression of plagioclase and titanite crystallization, as Matt mentioned earlier. But actually, the leptocaryocassiterase zircons overlap really nicely with the tin tungsten belt. So we have a smaller magnitude cerium anomaly, and we also have quite a distinct europium anomaly. So this is evidence, again, that we're looking at a drier system than we might expect. And if we look at the metal contents of these zircons, we can again see that this is tungsten. So tungsten is a metal that's typically associated with S-type magmatism. And we see variations of 5 orders of magnitude, of 6 orders of magnitude, of tungsten in these zircons. And all of the cores of these zircons, so the cores are in circles, the cores are all elevated in tungsten, whereas the rims show a variation between elevated tungsten and then very low tungsten as well. So it kind of suggests that actually this crustal body that we're looking at down here, rather than being a previous mantle magma, might actually be a S-type magma. So we're looking at hybridizing an I-type intrusion from our host body, and then also an S-type body that's at greater depth. And just to give you some geological context, this isn't wildly outrageous in terms of where we are in northeastern Greece. So this is the outline of the Greek coast, and this is the Moroni magmatic corridor in here. And this is the Rhodope core complex in a series of different domes trending from east to west. And actually these are exhumed to greater depths further west, and then they're becoming they're shallower and shallower the further east you go. But in the west here, you see S-type Cretaceous plutons. So it doesn't seem that far to suggest that actually there's an S-type Cretaceous pluton underneath the Ketros dome, but it's just not been exhumed because the level of exhumation is shallower in the east. So finally, the one thing I want to talk about now is looking at melt inclusions in zircons. And this again came about because the whole rock data for the porphyry intrusions was unusable, didn't make any sense. It wasn't sampling the actual magma, but it was sampling a very altered system. So we have melt inclusions in the zircons that range in size from they've probably generally got a diameter between 20 and 50 microns, and they form all sorts of different shapes. And they don't tend to be glassy, they tend to be crystalline. So what we've been doing in Bristol is trying to find a way of homogenizing the melt inclusions, making them glassy so that we can analyze a homogeneous glass. And there's also daughter crystals in these intrusions, whether they're daughter crystals that have crystallized from the melt or whether they were co-entrapment phases. I think you're unlikely to crystallize a wolframite crystal from a melt aliquot that's this big, but you might well have had a wolframite crystal sitting around in the magma chamber that you trapped at the same time as you trapped your melt inclusion. So if we look at the whole rock geochemistry of the intrusive suite, so the host plutons, and these are in pink in the squares. Then if we look at the whole rock geochemistry of the porphyries, in green in squares here, so they sit, so the porphyry samples sit at like 78% silica, and they fall quite nicely in potassium. I think that's just fortuitous, but they have absolutely no sodium left in them. When we plot on the melt inclusion analyses, they fall between 70 and 75% silica, and they fall nicely on a cogenetic trend with the whole rock geochemistry. We do have a few extraneous outliers here, and I think these might be sampling melt inclusions that have been vented and have actually been altered. So these are associated with fractures in the crystals, and where you get the hydrothermal fluids that can then get inside and can interact with the melts. And then we also have a bizarre population down here that I'm not quite sure of what the answer is. I have a few ideas, but we need to increase the number of melt inclusion analyses that we have before we can do much more. We can say much more. But we've been looking at laser data from the melt inclusions as well, looking at the metal contents of the inclusions. And you can see this is molybdenum versus tungsten, a really nice clear distinction between the whole rock host plutons, which have very little molybdenum and tungsten, and our melt inclusions are enriched in both metals. Whereas when we plot copper, we see that actually the melt inclusions themselves are no more enriched in copper than the host plutons. So these open symbols are where the copper is below detection in the porphyry melt inclusions. But I've put these on there to give you an example of this is the absolute maximum that these values could be, and that actually they're likely to be lower than this. So they're likely to be even less rich in copper than most of the melt inclusions themselves. And this carries on very nicely from what everyone's been talking about over the week, where we don't think that the copper enrichment in the melts needs to be anything particularly special to develop these systems. So in terms of the implications for melt inclusion analysis, this is very early stage work, but what we're able to do is get analysis of unaltered original aliquots of melts. We're able to get the minor and major element geochemistry and also have a look at the metals that they contain. And this is a high volume, low cost analysis, very similar to the way you'd have to mount up zircons for the trace element study. You can kind of fit this in that workflow very easily. But there's a lot more work that we need to do, so we need to increase the number of samples. I'm looking at a very different system, so it would be great to get some samples from an ARC type system. And then we might be able to assess the volatile budgets of the melts using techniques such as SIMS. So thank you for your attention. Does anyone have any questions?
Questions for Becky?
Thanks, Becky. Great talk. I wanted to ask about the S-type cores,
Yeah.
the late Cretaceous cores in the zircons. Do you think that that source material might have contributed some of the PGEs to these deposits? And do you think that you'll be seeing the same stuff in the late Cretaceous arc to the north?
I definitely think that's an idea. I've not really kind of gone anywhere towards testing that, but that's one of my thoughts, is that the PGEs and the semi-metals might be being sourced from these Cretaceous S-type granites. And certainly if you have these Cretaceous S-type systems in the Cretaceous arc further to the north, then yeah, they definitely might be contributing to the metal endowment there.
If you wanted some samples, we could definitely sort you out.
That'd be great.
Cheers. I just wanted to ask about your wolframite inclusions or daughters in those melt inclusions. So you imagine they're exsolving or crystallizing from the melt inclusion themselves?
No, I don't. I think they're co-entrapment phases.
Right.
Because I think to get sufficient tungsten in a little aliquot of melt to crystallize wolframite would be pretty impressive. And your metal concentration would need to be really very high.
Right, okay.
So I think they're co-entrapment crystals.
Could it not be, because you've got some melt inclusions that you think have been affected by late stage or post-crystallization fluid travelling through them, could these wolframite crystals not have formed during some late stage hydrothermal passage through that grain, if you see what I mean?
Yeah, so that particular crystal
think?
doesn't have any fractures in it, but that doesn't mean that they're not there. It's just what I can't see by the naked eye. So it'd be really great to get maybe some tomography or something to look at the structures leading to and from the melt inclusions to see if that would be a pathway for fluids.
Becky, I was interested in the tungsten data in the zircons you showed, and I seem to recall there may be an analytical issue with interference, as I think it's a zirconium dimer on tungsten. So I wondered if that was anything that you'd considered in those analyses.
So we did when we got this variation. One of the things that I did was went back onto the probe with the zircons, and we did some element maps. Turns out actually analysing tungsten on a probe is also very difficult. But we did manage to get, I think it was one of the K-beta lines, and we got an element map, and you can see very slight magmatic variations in tungsten. So I think we're fairly confident that what we're seeing is a magmatic tungsten signal rather than an analytical problem. But I do know that that's there.
Did the values agree between the probe and the laser, where you could detect them on the probe?
Yeah, to the same degree.
Any more questions? Oh, that's coffee time.